we can begin with 2 pieces of advice. Number 1, if you want to do well, do problems. And there's many problems out there. We have many old exams, many practice exams. I'll be posting another practice exam on Wednesday. There's just lots and lots of problems. Now, I don't want you to get caught up in doing too many problems, but do a reasonable number until you're comfortable. And if you see yourself struggling in a particular area, focus on those. The second point, take care of your health. This is going to be stressful. Now, we don't want it to be so stressful that it hurts you, so we want to make sure that you're taking care of yourself. That includes go outside, get some fresh air, eat some good food, drink plenty of liquids. Not right before the exam, but, you know, during the week. And if you need to scream into a pillow, that's fine. No problems, no problems. All right, so here we go. 12 problems. Number 1, solve for y. Given y prime minus y squared equals tangent squared x y squared plus secant squared x, and y of 0 equals 1. Now, we see a couple of things right away. First thing is that it's a first order differential equation because the highest derivative is the first derivative. And so that tells us, okay, we're in that first order sphere. So that's going to give us some information. We also see that there's an initial condition, and initial condition's coming at the end, but we're going to make sure we remember that the initial condition is there because after all, we've come for all the points. All right, well, since this is our first problem and we're dealing with first order, we say, what are our basic options? Our 3 basic options are separable, then linear, then exact, and coming in, and we should include it on our list, but it's not really a technique per se, is substitution. Now, substitution is just saying, can we rewrite things in a better way? Now, it may not always be obvious which one is right, but oftentimes you can look for certain clues. Right now, it's not linear. The reason I say that is for linear, you should have a y prime and a y. But we have y squared. Okay, so it's not linear. And exact, well, we kind of telegraph exact. You pretty much know when you see a problem, you'll know it's exact. And I know I'm not saying that well here, but when we get to one, and we will, you'll say like, yes, this is exact. You're telegraphing it to us. So I'm inclined to try separable. Okay, so here we go. Let's think about separable. Now, for separable, the goal is to separate. That's where the name comes from. And so we want to think about solving for y prime. And ideally, we get 2 pieces on the right-hand side, something which only depends on x, and something which only depends on y. All right, so let's get going there. So I'll move the y squared across. Y prime is tangent squared x times y squared. And I'll put a y squared right there. And plus secant squared x. Okay, well, it doesn't look like it factors, but that's okay. Looks can be deceiving. What can we do? What can we do? Well, looking here, we say, those terms both have y squared. So let's factor that out. So we have tangent squared x plus 1 times y squared plus secant squared x. And we start thinking, well, tangent squared x plus 1, is there anything that we can do with that? And maybe we recognize it, maybe we don't, but maybe we have a formula sheet on the back of our test. More than maybe, we do. And if you look on the formula sheet, let me find a marker that's a little bit darker here. You'll see that there's this nice fact that involves tangent squared and secant squared, namely tangent squared plus 1 is secant squared. So the great aha, we can replace this tangent squared plus 1 And now we're like, great. We have secant squared of x times y squared plus secant squared of x. And we keep going. Now what? I guess, any suggestions? Yeah, secant squared is common. So we have secant squared of x times y squared plus 1. All right, good. So now we're in that right setting. Y prime, something of x, something y, multiplied together. The reason we want to multiply is that the way we separate is we're thinking of y prime as dy over dx. And we're going to split the dy over dx. So think of the dy as something completely separate from the dx. And now we'll move things around. So we'll put the y's on one side. Dy over y squared plus 1. We'll put the x's on the other side. Secant squared of x dx. And that's our separation. So we are in a good setting. So for separable, what's the procedure? Well, step 1 is separate. Now, you might have it already given in something really nice where it's very easy to separate. You might have to do a little bit of work, which is what we did here. All right, what's step 2? Integrate. Separate, then integrate. All right, so there we go. So we integrate both sides. The integral of 1 over y squared plus 1 is arctangent. Some people are wondering, will there be arctangents? Well, of course, of course. All right, integral of secant squared on the equation sheet 2. It's tangent, n plus c. You only need one constant, so pick a side. Remember that constants can be absorbed, so if you had put a constant on both sides, you could just merge them into a single one. We know we should end up with a constant somewhere, because there's a first derivative. One derivative, one constant. Two derivatives, two constants. It follows a very nice pattern. Now, we want to solve for y. The reason we know we want to solve for y is because the problem tells us to solve for y. And so we say, all right, well, we're almost there. There's a single y, just get it outside of the arctangent. So we'll take the tangent of both sides. So y is tangent of x plus c. Now, are we done? No. No. We have to take care of our initial conditions. All right, so we're going to plug in 0 and 1. So we know that when we read this, this says when x is 0, y is 1. So 1 is tangent of 0 plus some constant c. Well, tangent of 0 is 0. That part goes away. So I'm looking for something where tangent of that value is 1. Well, that's a number that we've often seen. And it turns out that pi force works. Now there's many other things that work, but we just need one thing that works, so pi force. So our final answer, plugging this in, y is equal to tangent of x plus pi over 4. And we're done. All right, good. Good warm-up. Always nice to start off on a nice, simple warm-up problem. Any questions? All right. Well, then we move on to number 2. Find the general form. So here we don't have initial conditions. It's saying general form. Now, because it is general form, we want to make sure our answer involves a constant. It's not that you can find just any solution. You have to find all solutions. So we need to make sure our answer has a constant. Our differential equation says y prime plus tangent of t plus 1 over ty equals 3t cosine t. Now, this one you can basically almost instantly tell what it is. What is it? Linear. What gives it away that's linear? There's a single y prime and a single y. So if you see a y prime and just y separated, then you know we're in linear. So you say, all right, great. There's a procedure for linear. So what's the procedure? Well, the step one is check. Check what's in front of y prime. What needs to be in front of y prime? 1. It needs to be the 1. Because we're going to go through, now our goal here is to really say we're going to be making the left-hand side a derivative of something. And so we're building up to that. So the first thing is to make sure there's a 1. What if there was something else there, like sine of x, or I guess in this case, sine of t? Divide it out. Exactly. Good. Good. So we're all on the same page. Now, once you made sure that's a 1, you come in front of the y piece. This part is often in the formulas written as p of x. And what we want to do is find a multiplicative factor, an integrating factor. Now, I use rho of x. I know other instructors use mu of x. You can use whatever you like as long as you're doing the right process. So the process is we're going to take e to the integral of p of x. Now, as you do this, you will undoubtedly encounter logs. So make sure you know your properties of logs. We'll get there in a second. So for us, we're talking about, we have e to the integral tangent t plus 1 over t dt. You might notice here I used x's, here it's t's, and I should replace this with the t. It doesn't matter what the symbol is. Math, we're very flexible. We just realized, look, this is a stand-in for something. It's a shorthand. So it's the same process, t's or x's or whatever symbol you want to choose. All right. Well, we can integrate that. So this would be e, and the integral of tangent, look on the back of your formula sheet, is log secant. And the integral of 1 over t is log t. All right. Now at this point you don't need to worry about the constants. It won't change anything in the process. So you just say, look, I'll just choose my constant to be 0. So you want to be careful here, but you know, make sure you know your rules. So for instance, one thing you can do is you have a log plus a log. So you could say, oh, we could combine this. Log plus log is becoming multiplication inside. So we can think of it as log of t times secant t. And so then this ends up being t secant t. So we should be multiplying everything by t secant t. You can alternatively say this is e to the log secant t times e to the log t, and do it that way. There's several ways. As long as you get to the right place and use correct rules, you'll be okay. You'll be okay. All right, well, now we have our integrating factor. So what happens? Well, we're going to multiply everything by our integrating factor. So we're taking y prime plus tangent of t plus 1 over t times y equals 3t cosine t, and everything, both sides, all terms, gets multiplied by t secant t, this integrating factor. So that'll give us t secant t y prime plus a whole bunch of stuff, t secant t times tangent of t plus 1 over t times y equals, on the other side, cosine times secant is 1, because secant's 1 over cosine. 3t times t is 3t squared. Now you could, if you wanted to, spend some time multiplying all this out and saying, okay, what happens when you take t secant t times tangent t plus 1 over ty? Or you can say, look, I know what's going to happen. I know what has to happen. By design, in other words, 100% of the time, the left-hand side is nice. And in particular, the left-hand side is a derivative. It's a derivative of two pieces. One piece is the integrating factor. So this is our rho of t. And the other piece is y. And if you were to take this derivative and you were to be patient and multiply that out, you would see, in fact, that that's true. So that's why this works so well, is essentially, by doing this, we've introduced a derivative. Now, why is that so nice? Well, it turns out that derivatives are particularly easy to integrate. So we can now move to the integration step. And of course, when solving a differential equation, you oftentimes have to integrate at some point. So what's the integral of the derivative? Well, the integral of the derivative is just what it is. T secant t times y. The integral of 3t squared. T cubed. And now a constant. We don't have any initial conditions, so we don't need to worry about what the particular constant is. In fact, we want to keep it general. And we need to keep the c because we need the general form. So the last thing is, usually we want you to solve for y. So, all right. So what we can do is, we can say, oh, this is the same as y is t cubed plus c over t secant t. Now, you can simplify this. Dividing by secant is the same as multiplying by what? By cosine. So the first term, t cubed over t, makes it t squared cosine t. And then you have plus 1 over t, well, there's a c there, c times 1 over t times cosine t. And there's our nice general form. I see a question. I didn't think that this was that long, but yes, there are some people who memorize formulas. And if you wish to apply your awesome ability to remember things, that's great. But I ask that you write the formula down so we know, like, oh, this person didn't copy off their neighbor. Because we don't want to, that, you know, not that you would ever do that, but we just want to make sure. But yeah, that's fine. If you say, I know this formula, here's the formula, and I apply it. That's great. It's about the same amount of time. So you can memorize formulas or you can memorize processes. Unfortunately, I'm old. And so I don't have any more room left for formulas. See a question? Do you have to simplify? And the answer is no, unless it tells you to. So there's a generic instruction that's on the front of the exam that says, you do not have to simplify unless told. Now, that doesn't mean you can just stop arbitrarily. You have to stop at a point where you can say, yes, this is a correct answer. But once you have a correct answer, you can say, I have a correct answer. I don't have to simplify, and you can stop. Any other questions? I see one more question.
The second term there, that can't just become like e for a different constant. Oh, never mind.
Well, can't, yeah, so the question is, can't this become another constant? And the answer is no, because there's pieces that change. Yep. So constants have to be constants. If there had been a 5, the 5 could have been absorbed into the constant. All right. All right. 2 down. Don't worry, I'll pick up speed at some point. Number 3. Find an implicit solution to sine of y plus 5 over x dx plus x cosine y plus 3y squared dy equals 0, passing through the point e comma pi. All right. Gut instinct. You look at a problem like this, what do you think? And no, I'm not skipping this problem because I get to drop it. That's never going to be your thought. What type of differential equation do we have? Exact. Now, what gives it away? Well, for one thing, they oftentimes use the word implicit. If you see that, it's not a guarantee, but it's very frequently associated. But more particularly, the structure of the problem. So they almost always have the form of something dx plus something dy equals 0, or they might write it as something like ny prime plus m equals 0. Whenever you see something written in this very particular format, they're basically telling you, think exact. Now, the other thing that makes you think exact is whenever you look at it and say, sine of y and y squared, 5 over x and x. Whenever you see, like, the more complicated the expressions get in terms of the functions, the more likely it's exact, because exact is really good at that. All right. So how does exact work? Well, the idea here is we're trying to find a bigger function. And in essence, we're seeing some pieces of it through derivatives. So we say, okay, what's really happening here is this is the derivative with respect to the x. So whatever's attached to the dx, that's the derivative with respect to x. This part is the derivative with respect to y, because it's attached to the dy. So if I want the function, well, we integrate the two parts and compare. So sine of y plus 5 over x dx. And then we'll integrate x cosine of y plus 3y squared dy. Now this is the only time during our class, well, just about the only time, when we'll ever make an appeal to multivariable calculus. So it's not so bad. Even if you haven't had the course, the idea is pretty straightforward. Look at the dx, or look at the dy. That tells you what you're integrating with respect to. That says treat x like a constant. If you're not x, what are you? Sorry, treat x like the variable. I want to say that correctly. All right. Treat x like the variable. If you're not x, what are you? Constant. So what's this sine of y? So sine of y is a constant, so when you integrate, it becomes x times your constant. Integral of 5 over x with respect to x is 5 natural log of x. And then you have, not a constant number, but anything that's a constant with respect to x, so something which depends on y. On the other hand, for the other integral, say, okay, now we're integrating with respect to y. Y is our variable, and we treat x as like constant. So we have constant times cosine y. So the integral of cosine is sine, and then x comes along as a constant. Integral of 3y squared with respect to y, y cubed. And then some constant with respect to y, so that's anything which depends on x. Okay, so we said, okay, we have exact, we find our two pieces, we integrate our two pieces. Now comes a quick check. So you look at the parts which involve both x and y. So when I talk about parts, things separated by pluses and minuses. Yes?
Why didn't that first x before the sign for y?
This first x?
Yeah.
Well, because I'm treating it like a number. So if I integrate 5 cosine y, it would be 5 sine of y. And so since I'm treating it like a number, it's just a weird looking number. So it just comes along. So it stays as it is. All right. So you look at the parts that involve both x and y. So in this case, for the first integral, it's x sine y. For the second integral, it's x sine y. And what do we want to be true? We want these to be the same. So this is how you check for exactness. So this is a check for exactness. So you say, do these parts line up? In other words, does the parts involving both x and y from the first integral match the parts involving both x and y from the second integral? If they did not line up, what's true? Well, you probably don't have something exact. Go back to the drawing board. Now, this problem doesn't ask for a test for exactness, but if it did, this is where we can do it. Okay, now we know we're exact. So we're going to build up our solution. So the solution is the parts which overlap, in other words, both x and y. Then we're going to add in the only x parts, and that comes from the first integral. We're going to add in the only y parts, and that comes from the second integral, and that's our function which needs to be set to a constant. So we just work our way through the alphabet. We're up to the letter capital E. All right, so the overlap, what do we have? X sine y. The only x parts come to the first integral, and we say, well, the only x parts, 5 log x. The only y parts go to the second integral. parts only involving y cubed. And that needs to equal a constant. This is the general solution, implicit general solution. And you'd be very hard-pressed to solve for x or to solve for y. But that's okay, we don't have to. But what do we need to do? We have essentially an initial condition, a constraint. We have to pass through the point. Now when it talks about passing through the point, e comma pi, well, we know that means if we plug in x equals e and y equals pi, the equation has to be satisfied. So we just start plugging things in. So we have x is e, y is pi. So e sine of pi plus 5 natural log of e, because x is e, plus pi cubed, because y is pi, cubed equals e. Well, sine of pi, 0. Well, that's nice. Log of e, 1. 5 plus pi cubed. Yes, exactly, it's 5 plus pi cubed. Doesn't simplify, but that's all right. Constants don't always have to be pretty. So, putting it all together, we have x sine of y plus 5 natural log of x plus y cubed is 5 plus pi cubed. And we're done. All right. I did mention one test for exactness. Some problems they ask you to also provide a test or to verify that something's exact. It's not the only test. So there's one other test I want to point out. So if you call this first part, we'll call it m, and the second part you have n, then the other test for exactness, you only need one, but some people prefer it, so I'll just point this out, is you look at what's called m sub y, and you check, does this equal question n sub x, where the subscript means partial derivative. So if I come here, and I look at this first function, and I say, okay, what's the derivative of this function with respect to y? Treat x like a constant. Well, derivative of sine of y, cosine y. Derivative of 5 over x, 0. So we asked this cosine y equal question. Now come here, we're taking the derivative with respect to x, so treat y like a constant, and x is your variable. Derivative of x times cosine y is cosine y, because y right now is a constant, x is our variable. Derivative of 3y squared, 0. And does cosine y equal cosine y? Yes, so it's exact. So you either check the partial derivatives or you check the integrals to match. You don't have to do both. Dealer's choice, dealer's choice. I like to do the part where you do the integration because it just helps you get closer to the answer. Whereas doing the derivatives, it doesn't help you get closer to the answer. So that's why I have a personal bias. But you can use your own biases when it comes to solving problems. All right. Number 4. Find an implicit solution to the differential equation x squared plus 2xy times y prime equals 2y squared plus 2xy. All right. Well, not looking too hopeful. It's not linear. It's not going to be very easy to separate. But now, this goes back to, there was a fourth bullet point, which is substitution. So there's a few things that we want you to be able to recognize. Actually, I would say there's 3 things. So the 3 kinds of substitutions you should be able to recognize. The first one is called homogeneous. Now this has a different meaning when we got to later in our class, but homogeneous here just means everything has the same degree. Think of it as polynomials, everything has the same degree. Really the key is you can put everything in terms of y over x. The second substitution that you should think of is Bernoulli. And here your substitution looks like y to the k. It more or less looks a lot like a first-order linear differential equation, you just have this extra term with y to an inconvenient power. So those are the first two. The third substitution we want you to be able to do is one that we tell you. So if we tell you to do a substitution, we want you to be able to do it. So those are the three. All right, so let's try this out. Is this homogeneous? Yes. When we talk about homogeneous, same degree. So think of it polynomial. So this is degree 2. Here it's 1 plus 1, which is 2. Here's 2. Here again is 1 plus 1, which is 2. All have the same degree. So it's homogeneous. So that says, okay, first off, we're going to write everything in terms of y over x. So starting with your differential equation. So I'll copy it again. We're going to multiply both sides so that we end up with a y over x. And so the way we do that is 1 over x squared. So everything's going to have a 1 over x squared multiplied by. Now you might notice that this square here on the x squared matches the exponent we talked about when the homogeneous. We said, oh, degree 2, degree 2, degree 2, degree 2. And that's also degree 2. So multiplying this through, what do we have? Well, term by term. X squared times 1 over x squared, 1. 2xy times 1 over x squared is 2 y over x. And that's going to be multiplied by y prime equals 2 y over x squared plus 2 y over x. Now, the substitution that we're going to be making is the one that's indicated here. Z is equal to y over x. I like to think of this as saying y is equal to z times x, so that when we do y prime, because when we make a substitution, it's not just enough to replace the y over x's. We also have to replace whatever is involved in the derivative. So in this case, y prime. So y prime, well, okay, say we take the first times the derivative of the second, so that's z times 1, plus the derivative of the first, z prime, times the second, which is x. All right, so here we go. We're ready to do our substitutions. We have 1 plus 2z, so that's our 1 plus 2y over x becomes z, times y prime, which is z, plus z prime times x, is equal to 2z squared plus 2z. Okay, fun, good. Well, at this stage, a good strategy is start trying to get z prime by itself. Now, if you ever have a homogeneous problem, 100% guaranteed it's separable. And so you should think about trying to get to that stage. So a nice way to approach a separable problem is to say, okay, well, let's get, z prime equals the right-hand side, whatever it is. So what can we do? Well, let's get rid of this 1 plus 2z, or rather, instead of getting rid of it, we'll say we'll move it over. So that's 2z squared plus 2z over 1 plus 2z. We won't try to do any long division. Not yet. Not yet. All right. Again, a mindset here of trying to get the z prime by itself. Let's subtract z. Z prime times x, 2z squared plus 2z over 1 plus 2z minus z. Well, let's combine. So common denominator. So we'll multiply the second term by 1 plus 2z over 1 plus 2z. And if we do that, what do we have? Well, upstairs we'll have 2z squared plus 2z from the first piece. Then we're going to subtract z times 1, which is minus z, and subtract z times 2z, which is minus 2z squared. All of that over 1 plus 2z. Now, if we've lived a good, clean life, and our instructors like us, and they actually checked before they wrote the problem and gave it to us, Hopefully the third one is true, but not always. Good things will happen. The 2z squareds cancel. 2z minus z simplifies. This becomes just z. So we have it pretty simple now. All right. Good. Z over 1 plus 2z. And remember, on the left-hand side, we haven't done much to that. This is what? Well, we have an x, and z prime is dz over dx. So now we're ready to move things around. We'll separate. So we'll move the z parts on the far right over to the left, and we'll move the x parts over to the right. So this will become 1 plus 2z over z dz is equal to 1 over x dx. So we've separated. And after separation, integration. Good, good. So we are integrating both sides. All right. Well, the first part, notice you can break this up as 1 over z plus 2z over z is also known as 2. So 1 over z, integral of that is log z. Integral of 2 is 2z. On the other hand, on the other side, integral of 1 over x is log of x. And don't forget to throw in a constant. So because we are after an implicit solution, we could almost stop here, because what we have is certainly implicit, and it's certainly a solution. One small caveat: why is this not the right place for us to stop? Because of the z's. We introduced the z, not the problem, and so we have to get back to where the problem started. So the problem started in terms of y and x, so we say, all right, everywhere you see z, replace it by y over x, because z is y over x. So log of y over x plus 2 y over x is natural log of x plus c. And that is a perfectly valid place for us to stop. Yes?
Why would the z prime of x when it says equal to x dz over dx?
Right?
I don't understand.
Well, the x and the x.
Rewriting.
And z prime is dz over dx. So oftentimes if you're thinking separable, I find it very convenient to rewrite it. There's some subtle nuances that might come into play, but usually we think of, when we do a substitution, we're not changing the sort of the inside part. So we're still thinking of things as depending on our original variable. So our original variable was x, it still stays x. What we're changing is sort of the outside layer. So instead of y, it's becoming z. So originally this was dy dx. So we're still derivative with respect to x, but now with respect to our new variable, which we're calling z. Other questions? I see a question. Oh, do you need absolute values? This could be a very long discussion. And my response is no. Now, there's reasons to say yes, and there's reasons to say no. I will summarize it succinctly in the following way. When we're solving differential equations, things are actually a little bit more complex than we've let on. Yeah, so that's the answer. And so because really the tools we're doing work over complex numbers, and you don't need absolute value inside logs. And so that's the one response. I'm sure other people would argue with me, and I might, if this video successfully gets posted, I'm sure people are going to say, ha ha ha, I'm going to correct Steve. But, you know, I would say don't worry about that. I never grade for that. But now your question is, are you grading it, Steve? Not this problem.
I have a question.
Sure.
So what is the reason why we divided the differential equation by x squared?
So the question, okay, why did I divide by x squared? So essentially it was, I thought homogeneous. So when you think something's homogeneous, your goal is to say, make things look like y over x. And so right now, nothing looks like a y over x. But because of the fact that everything has the same degree, so in other words, 2, 2, 2, 2, where I say 1 plus 1 equals 2, then I say, oh, if I divide everything by x to that degree, then everything becomes a y over x. So that basically was like, because I'm thinking homogeneous, I'm shooting for y over x. That's why I did that.
So is that a general rule, whatever the order of the coefficient you have, you divide that by x to that code, like that order?
If it's homogeneous, yes. Now there are other ways to hide homogeneous equations. You can do things like log of y subtract log of x. But what can you do with that? You can put them together, because log of y subtract log of x is log y over x. So, but usually homogeneous more or less looks like that. All right. On to, a word problem. Good. Now, there are 3 potential categories for word problems, and nobody asked if there was going to be a word problem on the exam. And so I guess we'll just leave that as a mystery. But, okay. So, what's this one say? A 10-gallon tank is initially full of pure water. Okay, so this is a water tank problem. All right. Salt water is coming. At time t equals 0, brine starts coming into the tank at a rate of 10 e to the minus t gallons per minute with 4 ounces of salt per gallon. So this says, oh, we should draw a picture. Now, a good strategy is draw a picture, if you can, if it helps. And with tank problems, I find a picture helps me. All right, so we have our 10 gallons tank, and we have something coming in. And what do we have? Okay, so there's a rate. So 10 e to the minus t gallons per minute. This is just a reflection of saying it's not coming in at a constant rate. So initially it's coming in pretty rapidly, but over time it's going to sort of become less and less. All right, great. And we also have some, so this is a rate. There's also information about concentration. So there's 4 ounces per gallon. All right. At the same time, well-mixed solution from the tank will drain at a rate. So something's coming out at 10 e to the minus t gallons per minute. Determine how much salt will be in the tank as time goes to infinity. Okay, all right. So we have some information here. Okay, so let's start with some basic facts. Let's let S of t, this is just our convention, this is the amount of salt in the tank at time t. And let's see what we can say. First off, what's the amount of salt at time 0? And how do we know that? It's 0 because pure water. Pure water, no salt. All right. Now, the next thing for us to do is to work on setting up a differential equation. Now, the differential equation that we're going to have basically has more or less always the following form. The change in the salt, you look at the salt coming in, you add that and subtract the salt going out. Because salt can't, just spontaneously generate. It's not like, and in the 17th minute, the engineer said, "Let there be salt," and there was salt. No, that doesn't happen. If there's salt, it came from somewhere. And if it left, it went somewhere. So the only way salt comes in is through the inflow. The only way salt goes out is through the outflow. Okay, so we start saying, all right, well, what's going on? Well, for in, it's pretty easy. Because we say, well, you know the rate of, how much it's flowing, and you know the concentration, so you multiply these together, and the amount of salt coming in at any given time, 10 e to the minus t times 4. All right, that's pretty straightforward. The outflow is one you have to think about. Now, the first thing you think about is the water level. Is the water level in the tank going up, going down, or staying the same? Staying the same, good. Now, how do we know it's staying the same? We look at the rates, and we compare them. If the rate coming in matches the rate going out, the water level doesn't change. On the other hand, if that weren't the case, well, the water level would be changing. Okay, so that's good for us. So that makes things easier. So if we're thinking about this as a rate times a concentration, well, what's the rate going out? Still 10 e to the minus t. All right, no worries. So just to recap here, rate, concentration. Rate. Now, concentration. This one we have to think a little bit about. So how do you find a concentration? Well, you say how much salt is there total, and then you divide by how much fluid there is. Well, do we have anything that tells us the amount of salt in the tank at time t? Is there anything at all that tells us how much salt there is? Oh, S! It's right there. Brilliant, brilliant. And then we divide it by how much there is in the tank. Well, we know it's a 10-gallon tank and it's full. And we also know it never changes. So it's always 10. So, amount of salt, the amount of fluid. That gives us the concentration. Yes? This is the hard part. I see.
Now, what would we do if it were to change? How does that concentration change?
If what were to have changed?
Like, let's say the rate of change is decreasing or it's increasing.
Oh, sure. In other words, if the water level were going up or down, how would it change? It would change this piece right here. So the water level affects this part right here. And then you'd get something like 10 minus e to the t or something. And then it's like, oh, this looks terrible. So, yeah, so it's the initial amount, and then you add the rate coming in, subtract the rate going out, and then you multiply by t appropriately. So, but it's best to avoid that if you can. And in this case, we can. All right. Well, okay, so this is 40 e to the minus t, and then the 10s cancel, so subtract e to the minus t times s. And whenever you have a mixing problem like this, you're always going to get linear first order. So you say, great, we know we're back to linear first order. We did pretty well on that before, so odds are in our favor we'll do well again. So s prime plus e to the minus t times s is equal to 40 e to the minus t. Well, okay, what do? You check. Is there a 1 in front of the s prime? There is. Then you come to what's in front of the s. We're going to take e to the integral of that. All right. Well, the integral of e to the minus t is minus e to the minus t. So we have e, probably we should put some parentheses just so we don't get too confused, e to the power minus e to the power minus t. Now, does that simplify? No, not yet, but that's okay. It's all right. We have that expression. So, we're going to multiply. So when we do that, so we have our s prime times e to the minus t plus e to the minus t times e to the minus t s, I didn't give myself enough space, is equal to 40 e to the minus t, e to the minus t. Okay. That's not looking great, but that's just because I didn't give myself enough space. When we write it down and more compressed, we know, because of the theory, this left-hand side is automatically a derivative, namely of the integrating factor times s. So that part will be easy to integrate. It's this other hand, this other side, that's going to take us some work. But no problem. We should work a little bit. It makes us stronger. Integrate both sides. All right, the integral of the left-hand side is more or less automatic. So we have e to the minus t. Whoops, I keep putting my parentheses in different places, but that's all right. It's always true. Times s. Is this integrable? Great question. See, this is oftentimes we have the wonderful theory. In theory, we can always integrate it. In practice, can we? The answer is yes, we can. What do you do? By parts. Oh, someone likes a challenge. Substitution. Brilliant. You should always try a substitution first. Substitution should be your first thing. Now, of course, if it's something you can already integrate, then you just integrate. But if it's not that, try substitution. All right, someone suggested substitution, and I'm just going to follow their lead. Say minus e to the minus t. What would du be? E to the negative t dt. Well, wouldn't you see that? We have an e to the negative t dt. So this becomes the integral, the 40 still is there. We have e to the u du. And that is a lot better to look at. It doesn't make us nervous. 40 e to the u, or 40 e to the minus t. Okay, great. So, that's all work on the side. So we have 40 e to the minus t plus c. Okay. Now what? Well, we could solve for s. That's true. Now, technically, you can answer this question without solving for s, but I'd feel better if we did. Okay, so if you solve for s, what would you do? You divide by that, right? Now, notice that these are the same, so that's going to be a pretty easy division. Okay. We still have enough space. We'll finish this problem. Don't worry. So s is 40 plus c. Now, dividing by this, notice how there's a negative upstairs? What does it become on this right-hand side? So it becomes e to the plus e to the minus t. So you can think of it as this minus makes it 1 over e to the power e to the minus t, and then you move it across. I have to tell you, I kind of wanted this to be on the exam, but oh well, that's all right. At least we get to have fun with it together. It's sad that we didn't get to put it on. Okay, are we ready to answer the question about what happens as t goes to infinity, and why not? No. We haven't taken into account the initial condition. S of 0 is 0. Okay, so we plug that in. We have that 0 is 40 plus c. Okay, what do we have here? Well, it's one of these onion problems, right? There's layers involved and possibly some tiers. So, start up here. Plug in t equals 0. E to the minus 0, 1. Then we have e to the 1, which is e. So we get 40 plus c times e is 0. So c times e is 40. So c is 40 over e. Oh, sorry, negative 40. Thank you. Negative 40 over e. It's fun doing it in front of a live audience. They catch all my mistakes. Okay, so updating now. S is 40. Subtract 40 over e times e to the power e to the minus t. Now, is this our answer? No. But it is how much salt there is in the tank at any time t. We just need to say, let t go to infinity. All right, work through the onion. Think of t as a big number. E to the minus t will do what? So just the part upstairs. E to the minus t goes to 0. Then we have e to the 0, which goes to 1. So this goes to 40, subtract 40 over e. So that's how much salt there will be in the tank as time heads off to infinity. Do I do it? No. I'm not a physicist. So good question, though. Good question. Sometimes questions will say include units, and sometimes it won't. By default, I don't. But if I ever see a problem that says include units, then what I do is I don't until the very end, and then I just put it in. Because the nice thing about math is it does what you think it should do. So in other words, if we ignore the units at the end are what they should be. So we don't have to keep track of the units in the intermediate steps. All right, good. That was a good one. I like this one. Any questions? Nice action-packed problem. All right, we will see more word problems later on. Number 6, our halfway point. Verify that e to the 2x and x squared are solutions to this differential equation. Okay, so whenever you see something about verify, now verify can come in many different ways. Verify is actually a pretty broad tool, but when you see verify, what does that mean? Yeah, well, it means put it in, right? Put it in and see what works. Now, sometimes it'll say verify. Sometimes it'll say, oh, you're trying to solve for some, the right choice of R or something, or the right choices for A and B. That really is verify problems. It just means plug in. If you have solutions, you plug in and you see what does that tell you. Okay, so for part A, there's nothing profound here. So let's start with y1. It's e to the 2x. You write down the first and second derivatives because there's first and second derivatives. 2e to the 2x. y1 double prime is 4e to the 2x. Say, all right. Well, then we have x minus x squared times y double prime, 4e to the 2x, plus 2x squared minus 1 times y prime, which is 2e to the 2x, plus 2 minus 4x times e to the 2x. Well, everything has an e to the 2x. Might as well factor that out. And let's expand. So the first part, we have e to the 2x times 4. So we'll have 4x minus 4x squared. The second part, there's an e to the 2x times 2. So bring the 2. That's plus 4x squared minus 2. And then in the last part, we have plus 2 and, whoops, I wrote 4 at the front. It's 4x, sorry. 2 minus 4x. Now you might say, wait, how did you catch that error? Well, because what should happen? If you've lived a good, clean algebra life, what should be true? Everything should cancel out because we're supposed to end up with 0. So if you see something not canceling, you know mistakes were made. But that's okay. Once you know mistakes were made, you know you can correct them. 4x's cancel, the 4x squared cancels, the 2's cancel, equals 0, and that's the verification. So we're happy. Now, of course, we have to do it for y2, but now we know the process. You plug it in. All right, so for y2, similar thing. You have x squared. You look at y2 prime, which is 2x. You look at y2 double prime, which is 2. So we have x minus x squared times, and this is the part where I often may mess up. So make sure you put in y2 double prime and not y2. So y2 double prime is 2 plus 2x squared minus 1 times 2x plus 2 minus 4x times x squared. Well, expand. 2x minus 2x squared plus 4x cubed minus 2x plus 2x squared minus 4x cubed. And we check. The nice thing about verify problems, especially when it says just verify that these are solutions, they're free points. Because you just know you keep going and you keep finding your mistakes until it all works out, because you know what has to happen. Okay, so that's what you do for verify. All right, part B. Write the general form for solutions of the differential equation. Well, what do we have? We have two solutions. We know it's second order because the highest derivative is the second derivative. And so for part B, what it's really telling us, without saying the words, is superposition. Say, oh, okay, so we should do superposition. What does that mean? Well, it says you combine solutions because we have a linear differential equation. It's linear, and I should also point out homogeneous. So that's an important thing. So we have a 0 on the right-hand side. We'll do some non-homogeneous stuff soon. Say, all right, well, superposition says take any combination. A e to the 2x plus bx squared. Well, not any combination. Some multiple times the first plus some multiple times the second. And that's the general form. Part C. Find the Wronskian. And use this to determine the intervals where the solution that you just found is guaranteed to be unique. All right, so the Wronskian. So the Wronskian of two functions, and they tell us the functions, right? So we should make sure e to the 2x is y1, x squared is y2. So e to the 2x comma x squared. Well, it's a determinant. Two functions, 2 by 2 determinant. In the top row, you write the function. All right, great. What goes in the next row? Derivative. So it's 2 e to the 2x and 2x. Well, now you remind yourself that, oh, there's the two diagonals. So you just have to work on your two diagonals. So going downhill, you have 2x e to the 2x. Going uphill, you subtract that, you'll have x squared times 2 e to the 2x. And, well, we can pull some stuff out. We can certainly pull out a 2 e to the 2x, and then we have an x minus x squared. You say, all right, good. Now, what does the Wronskian tell us? If the Wronskian is always 0, it says, these are not different solutions, these are the same solution. That's very unlikely to happen, unless you do something quite silly. Where the Wronskian is 0 sometimes, but usually non-zero, it says, well, there's places where things start to break down. And you might notice something here. There's an x minus x squared. Looks an awful lot like that x minus x squared. Coincidence? No. No. And you might say, well, why is that so bad? Well, essentially, you have a 0 there. So if you were to make a 1, you'd have to divide by x minus x squared, but then you'd be dividing by 0. So that's why things tend to break down. So we say, okay, so first off, this is the Wronskian, which it asks for, said find the Wronskian, we did. And then we have to say about the intervals. So as far as the intervals go, you say, well, when is this 0? So for which values of x is this 0? Well, certainly not the 2, not the e to the 2x. What about x minus x squared? 1 works. Any others? And 0. So we say, aha, there's 0 and 1. So the intervals for which things don't break down, we have 3 of them. And so we can write them in a couple of different ways, and we're not testing you on notation. You can write them as, say, minus infinity up to 0. I would make it an open bracket, 0 to 1, and 1 to infinity. So that's one way you can write it. You could also write it as, say, x less than 0, 0 less than x less than 1, 1 greater than, 1 less than x. Oh, that's right, that's x greater than 1. Yeah. Both are fine. All right. Well, that's our halfway point. Any questions about this one?
Can you pull out 2x instead of 2x and just make the inside parentheses 1 minus x?
Absolutely. You could have pulled out a 2x at this stage. No problems. No problems. Number 7, a picture problem. Okay. So in the diagram below, f of y is drawn with a solid line. So there's a solid line here. And g of y is drawn with a dashed line. So there's a dashed line. Well, it's more like a dotted line, but we'll accept it. And we're going between -5 and +5. And there's a differential equation. Y prime equals g of y minus f of y. Find all critical points, draw the phase diagram, and classify critical points as stable, semi-stable, or unstable, semi-stable, or stable. Okay. Well, so this is what we would call autonomous. And the hard part is spelling this. But essentially it's y prime equals stuff with y. That's what we mean by autonomous. And you should channel your first derivative test. So channeling our first derivative test, we'd say, well, the critical points, this is y prime equals 0. Well, let's see, what does that mean? So instead of trying to get ahead of ourselves, we might say, because we might be saying, oh, that used to mean where do we cross the axis? Think about the problem. Our problem is g of y minus f of y. So that says we need that g of y minus f of y to equal 0, or we need g of y to equal f of y. So in terms of the diagram, what are we searching for? Where they cross, they overlap. So we start looking and saying, where do they cross? Well, they cross there, and there, and there. They touch, that counts, and there. All right. So we now know that there are going to be 4 critical points. All right. So let's go to the phase diagram. So we can just drop straight down. So we have 4, 1, -1, and -3. Yes? We just look for the intersections, because that's where things were 0. We found there were 4 places where they intersected, so those are our 4 critical points. Now the next thing that has to happen for us is we have to say, okay, what's the sign of the derivative? Is y prime positive or negative? Well, y prime is g of y minus f of y. So if g of y is above f of y, is g of y minus f of y positive or negative? So think, if you have a large value, subtract a small value, the result is positive. So if g of y is above f of y, g of y subtract f of y is positive. So we have y prime is positive here. Here, it's f of y is above g of y. So it's low value subtract high value. Or sorry, well, let's be careful here. Okay. Just pick numbers. So if I'm at 3, g of y is -1, and f of y is +1. -1 subtract +1 is a negative. So y prime is negative. All right, go to the next interval. Between -1 and 1, are we negative or positive? We are negative. Okay? Just think of what's happening at 0. So g of y is, again, -1. F of y is +1. minus 1, which is g of y, subtract plus 1 is a minus 2. So where the red line is on top, the derivative is negative, or if you like, the solid line, where the dotted line or the blue line in this diagram is on top, you're positive. Between negative 3 and negative 1, positive or negative? Are you positive? Yeah, you're positive, yeah. What about our last one? Positive or negative? Negative. All right. This was the tricky part, so it's good if you have questions to ask now about the tricky part. Because when it comes to, the process is never hard. It's all about find the critical points, test the signs. So it's just a matter of think about how you can figure out what the signs are. Sometimes they'll give it as a diagram. Sometimes it'll be functions. Sometimes it might be something else. But okay, now that we have the sign, we have arrows. Where we're positive, we go up. Where we're negative, we go down. You'll notice that the inequality sign, it actually matches. So when in doubt, just follow what the inequality sign says to do. Okay, good. We've drawn the phase diagram. So we're basically home free. The only thing left is to classify. So we have 4 points. Negative 3, negative 1, 1, and 4. Negative 3, you're moving away from. So if you move away, what are you? You're unstable. It's like unstable people. You want to move away from them. How about negative 1? Stable. Yeah, they're pretty good to hang out with. What about 1? Semi-stable. You're sort of half and half. On one side, you attract things towards you. On the other side, you repel things away from you. What about 4? Unstable. All right. And there you go. I will say historically, students like these types of questions. They do really well on them. If this is on the test, I hope you continue that tradition of doing really well. All right. Number 8. A paper company is managing an expanse of land on which it grows wood for harvesting. Well, yeah, that's what you'd need to do if you're a paper company. The tonnage of material to harvest follows the differential equation. Q prime is 1 over 1,000 Q times 100 minus Q, where Q of T is the number of tons available for harvesting at T years. Given that the company wants to harvest 80 tons of material in 40 years from this land, then determine how much material needs to be on the land now. In other words, what's the initial amount of material that needs to be planted at time T equals 0 to produce 80 tons after 40 years? There's a lot going on here. Or is there? Now, when you read problems, oftentimes I'm kind of just half skimming for things that look mathy. So I see that looks mathy to me, because I see a formula, and then I see a number 80 and a number 40, and I see there's like a T equals 0. So those are things that sort of catch my eye. So I would say if you see a word problem and you're panicking, first look for the math. And then you can start ignoring things that aren't important. Let's start with this formula. When we see this formula, is this telling us something? It is telling us something. What is it telling us? It's telling us logistic. So there's a model called the logistic model, which follows the formula for certain types of population growth. Now, it doesn't just have to be population, it's just a model for growth when there's limited environmental factors. So, for example, a forest can't grow arbitrarily large. Eventually, it starts running into the rest of the trees. Now, the generic expression is Q prime. Now, I will say, well, if I'm going to be really generic, usually it's written as like P prime equals K times P times m minus p. But for us, p and q, all right, whatever, just change the letter. They're right next to each other on the alphabet. It's perfectly fine to swap them. The good news is we know this really well. So this differential equation problem is not going to have very much differential equations involved. Because what? Well, for the logistic equation, we know, and of course we all have memorized this, that it looks like mp0 divided by p0 plus m minus p0 e to the minus k mt, right? Of course, of course. Now I know some of you are looking like, I think I don't have that memorized. But do you need to have that memorized? No, because it's on the formula sheet. Good. Okay, so, all right. So now we say, okay, let's just apply it to our problem. We just start identifying things. So for us, we have that k is 1 over 1,000. We have m is 100. We have that p0 is, we don't know. We're trying to figure that out. So we'll call it p0 for right now. That's what we're after. Okay, so we plug that in. So we have, well, go ahead and keep working here. 100, that's our m, times p0, divide by p0, plus 100 subtract p0, e, and then I'm going to multiply k times m. Well, k times m, 100 over 1,000, is going to make it 1 over 10. So e to the minus t over 10. So that's the formula that this wood is going to follow in terms of how much wood there is at any given time. What's our goal?
80 tons at time 40.
You want 80 tons at time 40. So we want that P of, well, we should switch to Q at some point, shouldn't we? All right, whatever. We'll stay with P. P of 40 equals 80. All right. We're solving for T, so if it makes you uncomfortable, you can switch back to Q's. So we say, okay, we'll plug in T equals 40 and P equals 80, and we'll see what we have. So we have 80 is equal to 100 times P0 over P0 plus 100 minus P0, e to what power? E to the negative 4. Now, we have one equation and one unknown. This is our favorite scenario. And I don't want to make it sound trivial, but what's left for us to do? Solve for P0. And once we have P0, what do we do with it? We put a box around it. Because it's going to be our answer, because that's what it's wanted. What's the initial amount? We needed to know P0. That was the whole point of this problem. And so we're pretty close. Well, I struggle with fractions. So let's cross multiply. So think of 80 over 1. So what do we have? We have 80 times P0 plus 100 minus P0 times e to the minus 4. Now the number is going to be a little bit messy, but that's okay. That's life sometimes. It's 100 P0. Okay. All right. Well, we can distribute here. So we have 80 P0 plus 80 times 100 is 8,000. And then we have an e to the minus 4. And then we have a minus 80 P0, e to the minus 4 equals 100 P0. All right. What comes next? Well, yeah, we can cancel. Let's move all the p0s across. And so we have 8,000 e to the minus 4. Now, we have 100 p0, subtract 80 p0, which is 20. And then here, minus 80 becomes plus 80 p0 e to the negative 4. Okay, well, we're pretty much home free. What's in common here? P0. In fact, we can pull out a 22. 20 P0 times 1 plus. Now here it'll be 4 e to the minus 4. What's the last thing for us to do? We're not yet to box. One step away. Yeah, isolate P0. So we're just going to move these other pieces across by dividing. If I take 8,000 divided by 20, what's that? 400 e to the minus 4 over 1 plus 4 e to the minus 4 is equal to P0. And we have our answer. Not the nicest number. If we had a calculator, we could compute it. But, of course, we don't have calculators. It's not that kind of a test. But we do want to make sure you know how to work with things. And we like to ask logistic problems from time to time. Keep you on your toes. But the good news, if we ask you, there's the formula. All right, any questions? We're about 2/3 the way through. Are you feeling okay? Or I hope this isn't making you nervous. All right. Well, we still have 4 problems. Number 9. Give the general form for solutions of y. And now this notation, it's not to the 7th power. That's the 7th derivative. The reason we use that is if we wrote down 7th derivative like that, people would start being like, okay, there's 1, 2. It's hard to see. So that's why we use this notation. So it just means 7 derivatives. So there's the 7th derivative of y plus 8 times the 5th derivative of y plus 16 times the 3rd derivative of y. Now this is one of our favorite types of problems. Homogeneous, linear, constant coefficients. This is algebra. All algebra. So we're going to do some algebra work. Now what does that mean by it's algebra? Well, there's sort of a diagram I draw. It says, okay, we have the ODE problem, and we have our ODE solution, and we're trying to get between the two, and we'll do it by taking the long way. Namely, we'll change it into an algebra problem. So instead of going straight, we're going to go around the box. All right, so that's sort of the intuition about what's going on. So how does it actually work? Well, the key here is we're going to turn this into a polynomial. And it's called the characteristic polynomial. And r, whatever the derivative is, that's the power. So r to the 7th plus 8, r to the 5th plus 16, r cubed equals 0. So the good news is the only thing left for us to do in terms of the algebra problem is to find the roots. The bad thing is this is a 7th degree polynomial. So we don't have a quadratic formula for a 7th degree polynomial. So we might have to think a little bit. What are some things that we can do here? Factor out. Yeah, we can factor out an r cubed because the lowest power is r cubed. That's r to the 4th plus 8r squared plus 16 equals 0. Okay, that's not bad. So now the r cubed we can probably handle. But we have something with an r to the 4th. So this is a classic trick. It's really hiding a quadratic in disguise. Think of this as r squared squared plus 8r squared plus 16. Because that's another way to think of r to the 4th is r squared squared. Or if that's a little hard, just introduce, say, well, let's say capital Z, Z squared plus 8 capital Z plus 16. Could you factor that? Does that factor nicely? Well, so we need two things that multiply to 16, add to 8, which are 4 and 4. So this becomes r squared plus 4 times r squared plus 4. Okay, so what are the roots? From this, we get 0, 0, 0. We have to include multiplicity. R squared plus 4. When does r squared plus 4 equal 0? Plus minus 2i. And again, we're going to have plus minus 2i. All right, so here are our 7 roots. Okay, so we took our ODE problem, turned it into an algebra problem, which means turn into that polynomial. It's called the characteristic polynomial. We started chipping away at it. Now, we're not going to give you something where you have to do long division or anything fancy. This is all going to be things which are, in essence, everything is a quadratic, or it's a kind of close to a quadratic, close enough that you can make it work like a quadratic. So don't panic about like, oh, I'm going to need something sophisticated. No, nothing sophisticated needed. Now, we have to transform our roots back to solutions. Okay, so 0, what does that correspond to as a solution? So our solutions they look like e to the rx, so e to the 0x, also known as 1. What about this second 0? Well, we can't use 1 again. It has to be something new. Every root needs to go to something new, so if it overlaps, we bump, which means multiply by x. Right, so x. How about this third 0? X squared. All right, so we have 3 solutions. We need 7. The reason we know we need 7 is the degree, or I'm sorry, the order tells us how many solutions we need. All right, plus minus 2i. Now, as a reminder, if your roots are a plus minus bi, then you look like e to the ax cosine bx, e to the ax sine bx. Now, you might say, wait, I thought we looked like e to the rx. And the answer is yes, that's true too. But what we do is, because so many people are scared of complex numbers, is we hide the complex numbers and they show up secretly inside the cosines and the sines. So for the plus minus 2i, what pair of solutions does this correspond with? So the a is 0, so there's no exponential, so it's cosine 2x and sine 2x. So that's that pair. What about this plus minus 2i? What is that going to do? It'll be cosine 2x, sine 2x again, but because we already have them, we add factors of x. So x cosine 2x, x sine 2x. Oops, I'm running out of space here.
Did the other bumps not affect that? Would it not go x third?
No, because the bumps are strictly within the same repeated roots. So because this set of repeated roots is for the zeros, this set of repeated roots are for the plus minus 2i. They don't interact with each other in terms of the bumps. So bumps only happen within the same root that's been repeated. All right, so is this our answer? No, because every time I've asked that, that's not the answer. Okay, so general form. So what we have here is we have 7 solutions. How do we go from 7 solutions to every solution? What's the idea? Sorry, what? Well, there's going to be 7 unknown coefficients. There's a word. Superposition. Now, we don't always write this down, but this is used a lot. It's used so often that we sort of like forget that that's what's going on. But superposition is what allows us to say, oh, we can combine. Their powers combined, they are the full set of solutions. So you just start working your way through the alphabet. Now, if you don't like the alphabet, you can use like C1, C2, C3, but just make sure you have something that indicates arbitrary value. So somehow it's a coefficient of some sort. So I have a plus bx plus cx squared, d cosine 2x, e sine 2x, f times x cosine of 2x, and g times x sine of 2x. It doesn't matter which order you write it in. You can write them in any order you like, but you need to make sure you have them all, because otherwise you won't have the general form. And that's the answer. All right. Any questions? Good. We might be out of here at a reasonable hour. That'll be my first time. Okay, number 10. You are designing a spring mass damper system so that with some mass of m equals 3 and a spring constant k equals 12, the system will be critically damped. What damping constant c do you need to order to achieve your result? So 2 orders says like you're placing an order. That's not a typo. All right. Well, we have a spring mass damper system, so that pretty much gives it away. There's no talk about external forces. So our underlying equation, mass times acceleration. So mass acceleration, that's a force. Our damping constant times the velocity, because the damper is based on how fast you're moving. And then Hooke's law is a constant times position. So C is called your damping constant, K is your spring constant, equals 0. Now, channeling what we just did, we said, well, this is like a constant coefficient, homogeneous, linear, differential equation. Turn it into the polynomial, and we say, well, our root should be, quadratic formula, negative c plus minus square root c squared minus 4mk all over 2m. Okay, nothing too surprising. Now we have to figure out what's going on. Well, we want the system to be critically damped. How do you know if something's critically damped? What's the sort of thing that must occur? Repeated roots. Repeated roots says that this part has to go away. So we now know that we need c squared minus 4mk to be 0. Or you could say c squared needs to be 4mk. Well, that's 4. M is 3 because it said m is 3. And k is 12. Well, so c squared is 144, or 12 times 12. So that says c is 12. All right. Good. Well, that's part A. That's part A. So, part B. Well, what do we have? When your damper arrives, you discover that the spring constant was accidentally misread. Whoa, not that that would ever happen. Ha! And had its digits reversed. So the spring constant wasn't 12, it was actually 21. If you use this damper in the system with the same m and k as given in part A, we should say our new k, then what will be the form of solutions for the behavior of the spring is this system undamped, underdamped, critically damped, or overdamped. Okay, so it's not the same k, sorry about that. All right, so what do we have? Well, we just fill in what we know. We know mass is 3, so we have 3r squared. Our damping constant we ordered was 12, so we have 12r. And then k is now 21. All right. Well, we want to solve. Is there anything we can do to make it simpler? Yeah, might as well. If you see something, do something. A lot of math is just successive simplifying over a long time. Well, we can try to factor. Okay, that didn't work. All right. Well, if you can't factor, no problem. You still have the quadratic formula, still holds. So we say, all right, plug it in. R equals, so in this case it'll be -4 plus minus square root 4 squared, which I'll write as 16, minus 4 times 1 times 7, all over 2. Well, -4 over 2 is -2, plus minus we have a half, 16 minus 28, -12. Well, not the nicest numbers, but it's not the worst. Can we do anything with -12? Well, 12 is 4 times 3. So you can pull out a 4, and when it pulls out of the square root, it'll cancel with the 2. So we have square root of 3 on the inside. What about the negative? What does that do? I. Oh, boy. So -2 plus minus square root of 3i. This is on the fringe of how messy we like things to be as answers, but not so bad. Okay, so what will be the form of solution? So notice we don't have to find a specific solution. We just have to find the generic form. We have complex roots, so that tells us that our pieces look like e to the minus 2t, the minus 2 coming from the real part, cosine of root 3t, the root 3 coming from the imaginary part, and e to the minus 2t sine of root 3t. So these are our two parts. So the spring, the form of solutions looks like superposition, a e to the minus 2t cosine root 3t plus b e to the minus 2t sine of root 3t. All right, so that's part of the question. The other part, are we undamped, underdamped, critically damped, or overdamped? What are we? We are underdamped. Now you can do it in a couple different ways, but basically, if it's still springy, you still see sines and cosines, that means that the damper isn't up very high. So it's relatively low. So that's an underdamping. When the sines and cosines disappear, that's when their damping is set too high. You're overdamped. So the fact that we see sines and cosines tells us we're underdamped. That plus, of course, we see some exponential functions, which means we're decaying. So we start going up and down, but over time, we go up and down less. And so there we go. Another way you can see it is look at the roots. So we have imaginary parts and real parts. And so when you have that, you're underdamped. Yeah, sure. This step. Sure. So think of square root of -12 as three things. You have a square root of a -1, a square root of 3, and a square root of 4. Because if you have -1 times 3 times 4, what do you have? You have -12. So the -1 square root gives you the I. The square root of 3 gives you square root of 3. The square root of 4 gives you 2 times a half, and that cancels. Yes? The system is undamped if there's no damper. So if C equals 0. So the nice thing is it basically all boils down to the damper. And so it's very easy to say undamped. Undamped, no damper, C equals 0. Any other questions? All right. 2 questions left. Our last topic, non-homogeneous. Number 11. find the solution to y double prime minus 3y prime minus 10y is equal to 60 e to the 2x plus 100x, satisfying that y of 0 equals 3 and y prime of 0 equals minus 2. Now, we have a couple of things. We have some initial conditions, so that's going to come in at the end. We also have stuff on the right-hand side, the 60 e to the 2x plus 100x. And so that part right there is saying this is non-homogeneous. Now, there's a couple of ways that non-homogeneous problems can be approached. They give us an answer. Unfortunately, it looks like they have not done that, so we're going to not use that approach. There's something called method of undetermined coefficients, and there's something called variation of parameters. If you have to choose between undetermined coefficients and variation of parameters, choose undetermined coefficients. And that's what we're going to do in this problem. But of course, you have to know, do you have that choice? So undetermined coefficients, it's very narrow. You can't always do it. So how do you know? How do you know? Well, you look at that left-hand side and you ask yourself the question, is this a constant coefficient linear differential equation? Yeah. You look at the right-hand side and you say, does that look like what comes out of a constant coefficient linear homogeneous differential equation? And if in both cases the answer is yes, you can proceed. Okay, so what's the framework here? Well, the basic idea is to say that our solution has the form of two pieces, yc and yp. So C stands for the complementary solution, P stands for a particular solution. So we start by saying, in step 1, find yc. You always do that. All right, so we start by finding yc. And how does that work? Well, this is the same as saying, make your f of x 0. So y double prime minus 3y prime minus 10y equals 0. And we're back into things that we've been doing for the past few problems. We're going to go into algebra. R squared minus 3r minus 10 equals 0. So y becomes r to the 0. So that's why it's 10. It's not 10r. And we say, well, does it factor? Well, does it factor? It does. What does it factor as? So r minus 5, r plus 2. If in doubt, we try it. R squared, check. 2r minus 5r minus 3r, that's good. And minus 5 times 2 is minus 10. If you can't factor, that's okay. Quadratic formula will get you where you need to go. So what are our roots? 5 and negative 2. So these become solutions. And in particular, well, this becomes e to the 5x. This becomes e to the minus 2x. And so your complementary solution is a linear combination of them. So here's our y sub c. All right. So we finished with step 1. Good. Now we move on to step 2. Step 2. We're going to find y sub p. Now, we have a particular method in mind. So this is undetermined coefficients. And I wish they chose smaller words. But okay, undetermined coefficients. So how does undetermined coefficients work? Well, you just sort of channel the song. We're making a list, checking it twice, gonna find out which points are nice. Okay, so here we go. We're making a list. We start by looking at the non-homogeneous part. And we grab the functions. From the first part, what's our function? E to the 2x. From the second part, what's our function? X. Okay, so that's step 1. Grab your pieces. Step 2. All right, so I'll just keep track here. Grab your parts. Grab parts of f of x. Step 2, you say, okay, if I have any powers of x, I have to work my way down. Do I see any powers of x? There's an x. So if I have an x, what else do I need? A 1. All right, add in lower powers of x. Now there might not be any, but you have to check. That's the next thing. After you've done that, the next part is look for sine-cosine pairs. And make sure that they come in pairs. Do we have any sine-cosine pairs that are missing something? No, because there's no sine-cosines at all, so we're fine. What's the last thing that you have to check? Well, check for overlap with YC. Now, in other words, look at everything on your list and compare it to the functions, e to the 5x and e to the minus 2x. Are any of these functions any of those functions? No. No overlap, best possible outcome. If there were overlap, what would you do? And the answer is not to skip the problem. The answer is, if so, bump. Now we're not bumping everything, just the parts that overlap up until there's no more overlap. But we can't, if we had 3 functions, we still have to maintain 3 functions. All right, so that's sort of a quick rundown. So from this, we say, okay, our y particular has 3 pieces involved. So we know that yp looks like a e to the 2x plus b times x plus c. So I'm grabbing my pieces. Is this yp? And why not yet? Yeah, it's yp for some very particular ABC. But until you know what ABC are, you haven't actually found yp. So we have to find what A, B, and C are. So how do we do that? How do we find A, B, and C? We don't just point and say, they're there. We found them. No, that's not how it works. What do? Plug it in. Exactly. So this is sort of the verify idea. Verify is used a lot. So we're plugging it back into the original differential equation. All right, yp prime. So that's 2a e to the 2x plus b. Yp double prime is 4a e to the 2x. So here we go. Very patient. Because you don't get points for finishing 20 minutes early. You get points for finishing with correct answers. So don't try to be like, haha, I'm going to finish before everybody else. No. Finish at your pace. Okay, so yp double prime is 4a e to the 2x. Subtract 3 times yp prime, that's 2a e to the 2x plus b. And subtract 10 times yp, a e to the 2x plus bx plus c. All right, so we found the form for our particular solution. We're starting to plug in. After you plug it in, the next step is to gather. We're hunter-gatherers at this step. We're gathering by functions. So, what functions do we have? Well, we have e to the 2x. Say, all right. What is attached to e to the 2x? We have 4a, subtract 6a, because that's parentheses, remember that distributes, and minus 10a. Well, they're a's combined. Let's see, 4a, subtract 6a, subtract 10a is minus 12a. Yes? Yeah. You double check, right? Double check. You should get nice numbers. If you don't get nice numbers, something happened. All right, how about x's? Let's do x next. And you'll see that our gathering is the same functions we had here that were on our list. Okay, so for x's, there's actually just one place where there's an x. So there's a minus 10b. All right, last, the constant, 1. Okay, so we have minus 3b and minus 10c. All right? Now, what does this need to equal? It's a solution, so it has to equal the right-hand side. So this has to equal e to the 2x times 60 plus x times 100. Now you might say, well, wait, what about this part? Well, since there's nothing there, what does it need to be? 0. All right, so we have some equations. Minus 12a needs to equal 60. So a should be what? Negative 5. Minus 10b has to be 100. So b should be negative 10. Now we know what b is. So minus 3b, which would be 30, minus 10c has to equal 0. So c should be 3. So, updating. We now know that y sub p is a, which is negative 5, e to the 2x, b, which is negative 10 times x, plus c, which is 3. Okay, so there's our y sub p. All right. Good. Whew. We've done a lot of work. We would get a lot of partial credit here. But we're not going for partial credit. We're going for all credit. All the way. All the way. Okay, so what do? Well, we put them together. So we're now at sort of stage 3, which is write down your general form. So this is our general form. So we know that generically we look like some constant e to the 5x plus some constant e to the minus 2x minus 5 e to the 2x minus 10x plus 3. I will say on a side note, this was somewhat, I should have used different symbols for A, B, C here than this A and B. These A's and B's are not these A's and B's. But that happens. Okay, now, is this our answer? And why not? We have to solve for A and B because initial conditions. So we got to get those initial conditions taken care of. Now we have a y. We also have a y prime condition, so we'll take that derivative really quickly. 5a e to the 5x minus 2b e to the minus 2x minus 10 e to the 2x minus 10. So y of 0. Well, that's got to equal 3. But it also equals a, e to the 0 is 1, plus b, e to the 0 is still 1, minus 5, minus 0, because 10 times 0, plus 3. So that tells us that a plus b needs to equal 5. Y prime is 0, has to be negative 2. All right, we plug that in. We'll have 5a minus 2b minus 10 minus 10. All right, well, so 5a subtract 2b, well, I'm going to bring 20 across. There's a minus 2 there, so that'll be 18. 5a subtract 2b needs to equal 18. 2 equations, 2 unknowns. You're going to see this at some point. You might see this at a couple of points, so you want to make sure that you see 2 equations, 2 unknowns. You're like, in my sleep I can do this. What do we do? There's lots of ways. You can solve for a variable and substitute. I like to get cancellation. I see that I could cancel the b's pretty easily if I multiply the first by 2 and add. 2a plus 5a makes 7a. 2b and not 2b makes 0. 10 plus 18 makes 28. So what is a? A is 4. Well, we know that a plus b equals 5. So 4 plus b equals 5. So b is 1. So our final answer, our real final answer, y is equal to 4 e to the 5x plus b, which is 1 e to the minus 2x minus 5 e to the 2x minus 10x plus 3. Okay. Whew. We fit it on a page. That's always the goal, right? Okay. There's lots of steps. No single step is too bad. The YC, okay, our algebra, YP, make your list, get your form, plug it in, solve for your coefficients, and almost always the coefficients are fairly straightforward. Put it all together and solve for initial conditions. That's a lot of parts, but still, nothing's too bad. All right. I know we're basically out of time, but let's finish it. We've come this far. We can't leave without seeing the last one. Number 12. Find the general form for solutions of y double prime minus 3y prime plus 2y is 2 e to the 3x over 1 plus e to the 2x. Now, it is true that the left-hand side is nice, but it is also true that the right-hand side is what we call not nice, meaning it's not coming out of a differential equation, which is constant coefficient, linear, and homogeneous. So, if this is not nice, or the coefficients are not nice, we don't have a choice in what we do to find our y's to p. So this is variation of parameters. So that's what we're going to have to do on this problem. Now, there's a formula. It says y is minus y1. You can even say yp, but it's y. Integral y2 f over Wronskian y1, y2 dx plus y2 integral y1 f over the Wronskian y1, y2 dx. Okay, so there's this formula here. Now, what do you do if you didn't memorize that formula? Yeah, it's on the formula sheet. So you don't have to memorize this formula, which is great. It just means you just have to know how to use it. You say, okay, well, I have to understand what's going on. So the process is, it still starts out the same, right? We still have y looks like yc plus yp. That's still true. We still find yc first. So that's our first step, find our yc. And it still means you set f of x to 0. So for us, we now have y double prime minus 3y prime plus 2y equals 0. And I should add that this part right here is f of x. So this becomes r squared minus 3r plus 2 equals 0. Does that factor? Yeah, r minus 1, r minus 2. So our roots are 1 and 2. Well, okay, so that says one of our solutions is 1 and one of our solutions, well, suspiciously, I'm going to put it as e to the 2x and e to the x as our two solutions. It doesn't really matter. No, I changed my mind. I'm going to go with e to the x and e to the 2x. Yeah, it doesn't matter. It doesn't matter. I'm not going to be suspicious. But now that I've said I'm not suspicious, it's made me even more suspicious. Okay, so yc is some combination of these. But the important thing right now is that we have these functions which are y1 and y2. The y1s and y2s that you see here are these y1s and y2s. You have to make a choice. And as soon as you've made a choice, you have to stick with it. All right, cool. So the next thing for us is we say, well, we've got to fill in the pieces here. There's our Wronskian. So let's do that next. So the Wronskian, e to the x, e to the 2x. All right, well, we've mentioned Wronskian before. You put the functions in, you take the derivatives, that's e to the x, 2e to the 2x. You do your diagonals, and when we do that, what do we get? Well, we'll get e to the x times 2e to the 2x, which is 2e to the 3x, subtract e to the x times e to the 2x, which is e to the 3x, or e to the 3x. Okay, so that's the Wronskian. Now, we're almost ready. We have our y1, our y2, and our Wronskian. Do we have f? Well, I said this was f. You should be ever so careful. Before you jump in and say, yes, yes, oh, totally, that's f. What should you be careful about? Is what's in front of y double prime 1? If it's not 1, you don't have f. So the formula assumes that this is a 1. So for us, we're good to go. If there'd been like, I don't know, x squared or something, what would you do? You'd divide through, and then you have your f. All right, now you have your pieces. And so the rest of it, it's just a matter of carrying it out. Okay, so you found your y1 and y2 in your complementary solution. You found your Wronskian. So I'm just going to work through these integrals. So first integral is y2f over the Wronskian of y1, y2. Well, okay, so y2 is e to the 2x. The f is 2e to the 3x over 1 plus e to the 2x. The Wronskian is e to the 3x. They both have e to the 3x's. Well, that's very convenient. Almost as if it was planned. And by the way, it was planned. These ones are never accidents. 2e to the 2x over 1 plus e to the 2x dx. Can we integrate that, and how? The answer is, yes, we can. This part, if you think of this as your u, what is this part? Derivative of 1 plus e to the 2x? 2e to the 2x. It's du over u. So what does that become? It becomes a log. Log of u, or in our case, log of 1 plus e to the 2x. And we'll toss on a plus c. Why not? We can do that. All right. Now, a word of warning. This next step is slightly more sophisticated than what we would probably have you do, but it's not very sophisticated. So I don't want you to think like, whoa, this is super sophisticated. But if you're like, oh, I would never be able to come up with this on a test. We would never ask you on a test. We just do this for the fun part, for practice. For the test, we make them more straightforward. All right, whoops, I forgot my dx up here. Okay, so now we do our second integral. It's the same, other than we swap. So we're replacing, instead of y2, we're putting in y1. So we have e to the x, 2e to the 3x, over 1 plus e to the 2x, over e to the 3x, dx. Well, again, the e to the 3x's, they'll cancel out. So we have 2e to the x over 1 plus e to the 2x. All right. Can anybody see how to do this integral? If it helps, think what would Steve do? What would Steve do? WWSD. Steve would want it there to be an arctangent. Good. You've learned. If you set u equal e to the x, what's your du? E to the x. So what you have upstairs is 2 du. But what does e to the 2x in terms of e to the x? it's u squared. So e to the 2x is e to the x squared. All right, so what's that integral? Well, we already said it. It's 2 arctangent u. Which means that the integral that we were doing up here is going to be 2 arctangent e to the x plus some constant. All right, now we just have to put it all together. So here we go. We have minus y1, so minus e to the x times this integral, log of 1 plus e to the 2x plus c, plus y2 e to the 2x times the integral we got here, 2 arctangent e to the x plus d. And if you distribute this out, you end up with minus e to the x, natural log of 1 plus e to the 2x, plus e to the 2x times 2 arctan of e to the x. And then you have a constant e to the x. Now the minus doesn't do anything, so I'll just write it as some constant e to the x and a constant e to the 2x. All right, what's our next step? You are correct. We're done. Not just because we're tired, and this is the last problem, but we actually have this part is the particular solution. And what is this? It's the complementary solution. And you put them together, and that gives you the general form. If you hadn't included constants, you would only end up with the particular solution. Then you'd have to add back in the complementary solution. All right. We're done. Thank you for being patient.